Okay, so we're going to do chapter 6.4, which is looking at more specifically at logarithmic functions and their graphs instead of where we did 6.3 and their relationship to exponential. So as a reminder, your logarithmic function is the inverse to an exponential function. I always remember it by going the base to the exponent gives you the answer. And the reason I use base is because it's a lot easier to remember log of the base, and then the a and the x switch. So that's how I remember it. You can remember it with those letters. You can remember it with these letters. It doesn't matter to you. The big difference is that they're inverses. If you are graphing the logarithmic function, so here in red, we have the exponential function, and in blue, we have the logarithmic function. So they're a reflection over y equals x, which shows graphically that they're the inverse. And the same thing happens when you have a blah, 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 blah. When you have a fraction as your base. Here's your exponential. Here's your log. There's y equals x, still an inverse. So here's your function capsule. When you have a base that is greater than 1, it's going to be an increasing function. Notice the points that are on every part in every log. Same idea as the exponential ones, you just switch your x and y. So you're switching your x and y. Same thing when it's less than 1, greater than 0, less than 1. It's decreasing, and it's the same points as the other log. Just remember with the exponential, the x and y switched, which is your reflection. So domains. If we look at the logarithmic function here, our domains are always positive. They never cross that y-axis. So to find the domain, we need whatever is our argument to be greater than 0. So for this one, we'd add 1 to both sides. X is greater than 0. And in our interval notation, that would be 0 to infinity. For this one, all we're worried about is the argument of the log. We don't care about what's outside of the parentheses because that doesn't affect our domain. So this one is just, oh, that should be 1. This is 1 because 0 plus 1 is 1, not 0. Over here, x is greater than 0. So this is our 0 to infinity. This had a 1 inside the parentheses. This one didn't. That's why the domains are different. Okay, same idea here. We're going to take absolute value of x. Has to be greater than 0. Well, that's always true because whatever you put in the absolute value comes out. So the only thing this can't be is 0 because the absolute value of 0 is 0. So we would go negative infinity to 0, 0 to infinity, and then in parentheses showing it can't actually equal 0. Now if we look at this one, x squared minus 4 is greater than 0. Bring 4 over. X squared is greater than or equal to 4. So we take the square root of 4 and we get positive and negative 2. So we've got to test some intervals. Negative infinity to negative 2, negative 2 to 2, and 2 to infinity. So if I test negative 3 in our original equation, that comes out to 5, which is greater than 0. If I test 0, that comes out to a negative number, not greater than 0. If I test positive 3, it comes out to 5, also greater than 0. So we'd use those two intervals to do our domain. So even though we're using a different kind of function, the process is exactly the same as what we've been doing all throughout the book. Now we don't need to worry about those. All right, so for graphing the function, you can use your function capsule to do it, or you can use your calculator. So log base 2 of x minus 1. If I were to put this, wow, that's not what I wanted to do, in my calculator, this is going to shift it to the right. Wow, I'm having some serious issues with this. Okay, so just like regular transformations, it's happening to the x, so it's going to move us to the right 1. So if our log 2, if our log looks like this, it would move everything to the right 1. Another way to do it, if you're not sketching and you're actually graphing it, is you're just going to plug in different points to the equation and graph the points you get. So if you plugged in 5/4, you'd get -2, graph that point. Plugged in 1.5, you get -1, graph that point. You can do that with any function. So if you graph this one, what would happen? What's the transformation that happens to this graph? It's going to go down 1. Good. It's outside the parentheses, so it goes down 1. So now I'm going to go back to this one and talk about the asymptote, the x-intercept, the domain and range, and if it's increasing or decreasing. So if we look at this graph, the asymptote is 0 in the standard one. So since we went right 1, our vertical asymptote would be x equals 1. Domain starts at 1, goes up forever. Range, arrows on both ends, so -infinity to infinity. What else does it ask for? And then increasing or decreasing? Well, as you go to the right, it goes up, so it's increasing. So now if we look at this one, log base 3 of x minus 1. So if we look at the graph, it didn't go left or right, so our domain is 0 to infinity. Arrows go up and down, so the range is still -infinity to infinity. Since the domain is 0, our asymptote is x equals 0. And then it's increasing. So all of that is the same stuff we've been doing. You can also figure out your asymptote, just like we did before. You don't want your argument to be inside. So when we figured out your domain, that gave you the asymptote. So if I go back to this screen, if here 0 is what it can't equal, that means our asymptote's x equals 0. For this one, there's 2 things it can't equal, so our asymptotes are going to be -2 and +2. Same exact process we've been doing. Instead of being the bottom of the fraction, it's going to be what's inside. Your x-intercept is where the equation equals 0, so you set it equal to 0 and solve. Just because we're dealing with exponential and logarithmic functions, the process is exactly the same as it's been all along. So show the graph of each function is symmetric with respect to the y-axis. So you could put it in your calculator and see the graph and say, yep, that's symmetrical. Or if you remember, to be symmetrical over the y-axis, f of x has to equal f of -x. So we could just plug in, so f of -x, I plug in -x inside the absolute value. Well, what's the absolute value of anything? Spits it out positive. So those would be the same thing. They both give you a positive number, so that is symmetrical. So let's do this, f of -x. Well, what's -x squared? Positive. So this ends up being the same thing, so that's also symmetrical. So if you plugged in -x and you got something different, wouldn't be symmetrical. That's all that's telling you. That's the one we just did. Okay, so how to graph this. Before we read this, we're multiplying inside with the x. So it would look like this is going to be a stretch. But if you think back to the product rule, it's like saying log 8 plus log x. Log 8 is going to be a number, so it's going to shift it up 8. That's what that whole mess says there. Once you break it apart, you have a number, so you're shifting up. Inverse function. So we're going to start the same thing. Rewrite it with f of x as y. switch the x and y, so x equals. Now we want to get our exponent alone, so I'm going to subtract 3 from both sides. It's always good to divide by that -1, just to keep it positive. So we'd have negative x minus 3 equals 2 to the y. Now we're going to do the log. So remember, base, the exponent equals a, log base b of a equals x. So our base is 2. So we're going to write log 2. The answer on the other side is what goes in there. So if we distribute this negative, we have negative x plus 3, and that's going to equal y. And then you rewrite it as f inverse of x equals log base 2 negative x plus 3. So same process, we're just using that log inverse information. So here is what the exponential function looks like. Your domain and range, what the log would be if you plugged it in, so you get your x-intercept and your asymptote. Then if you do the inverse, the domain and range switch. That's what inverse functions do. X and y intercept switch, asymptote, the horizontal becomes the vertical. So that 6.4, I went through it really quickly because it's all the same kind of stuff, just looking at it in other equations. Email me if you have any questions.